In the vastness of our universe, hidden within the cosmic tapestry, lie celestial oddities that challenge our understanding of reality. Today, we embark on a journey into the enigmatic realm of black holes. Much has been said concerning the mysterious black holes. Some of it describes observations, and some is speculation or even science fiction. This video explains what is observable and what is known and rules out several popular black hole ideas. We review the top 3 out-of-date ideas at the end of the video, so stay to the end. Let's begin with what we can observe. We see using visible light or other wavelengths using special telescopes. A black hole is an area in space that no light appears to leave or pass through. The absence of light passing through or originating from a black hole defines it. That means they are invisible to us. However, from observing how these black areas interact with their surroundings, we can better describe what is not seen. Black holes' gravitational fields interact with their surroundings. This interaction is not just theoretical. Observations of star orbits and curved light are solid observations astronomers have made. Further, the incredible image the Event Horizon Telescope captured has brought the reality of black holes into focus. When discussing black holes, we could define them by their observable gravitational effects. These are the event horizon and how they act as gravity centers for orbiting stars. First, we consider the event horizon. Most black holes are thought to be born from massive stars that exhaust their nuclear fuel. The gravitational collapse that follows forms an object so dense that nothing, not even light, can escape its gravitational pull. A black hole's gravitational field is stronger than the phenomenon that propels light forward. Thus, light photons are trapped and do not leave it. We perceive it as black with no light. Like all celestial bodies, a black hole's gravity field becomes less effective at greater distances. Eventually, there is a distance where the effective gravitational field weakens to be less than the phenomenon that propels light forward, and light escapes. This distance from the black hole's center is called the event horizon distance. The event horizon distance forms a spherical shell area surrounding the black hole's center. The light inside the sphere cannot leave. The light outside of the sphere can leave and go onward. Light approaching the black hole within the event horizon enters and cannot escape. The light just outside of the event horizon can pass by the black hole and continue on its journey. So a black hole has 2 components. It is the body causing the strong gravitational field. It is also the extent to which the gravity field can trap light, the event horizon sphere that surrounds the body. Usually we refer to the central body and the event horizon as the black hole. The event horizon is observable. The event horizon creates a spherical outline when looking at a black hole with the telescope. It divides what cannot be seen with what is outside the black hole's event horizon. It shows us the minimum distance light can move past the black hole. I hope you are enjoying this video so far. The video is brought to you by the new book, Cosmology's Best-Kept Secrets. In the description, you can click for a free book that offers discoveries that better explain the universe. Check the description for the free book copy. Now back to the black hole mystery. How a black hole's gravitational field acts on neighboring stars gives additional information about the black hole's central body. One remarkable observation involves the orbits of stars around supermassive black holes at the center of our own Milky Way galaxy. There, several stars orbit the supermassive black hole called Sagittarius A. Through meticulous observations spanning 30 years, astronomers have photographed the precise motion of S2 and other stars, revealing the orbits around this black hole. The star's movements and sizes provide an opportunity to estimate the strength of the black hole's gravitational field and the mass of its central body, causing the stellar orbits. By studying the orbiting stars, astronomers estimated Sagittarius A's mass to be equivalent to 4.3 million suns. Its event horizon is estimated to be 24 million kilometers in diameter, which would fit inside Mercury's orbit around the Sun. In the case of Sagittarius A, the observed orbits of stars like S2 suggest that the gravitational field is spherical and symmetrical. Such a gravitational field suggests the central body causing this black hole effect is a single extremely massive spherical object located at the center. Other supermassive black holes are much larger. For instance, astronomers used the Event Horizon Telescope to photograph the supermassive black hole in the galaxy M87. They estimate its mass to equal 6.5 billion of our Sun. They say its event horizon diameter is about 40 billion kilometers. That is Pluto's orbital distance times 4. How could we reason what type of celestial body is in its center that creates the intense gravitational field? Let's work our way up to the gravitational field of a black hole and why it is special. If we start with the Moon, it is small. Its amount of mass and its gravitational field are small. Its gravity is so weak that it cannot hold gases near its surface, and they all move to the surrounding emptiness. The Moon has no atmosphere. Mars is 60% the size of the Earth. It has a stronger gravitational field than the Moon, but less than the Earth's. Mars can hold heavy gases like nitrogen, carbon dioxide, and argon near its surface, but not lighter ones. Thus, oxygen, helium, and hydrogen float away to outer space. Because of its size and gravity field, Mars will never have an atmosphere that can sustain humans. Earth is larger, and it can hold oxygen near its surface. That makes human life possible. Much larger are gas giants like Jupiter and Saturn. The size and gravity can hold helium and hydrogen gas. Thus, the accumulation of these gases, their gravity causes a substantial influence within their immediate vicinity. However, these gas giants are not massive enough to have enough internal pressure to cause fusion. The Sun is a much larger collection of gas. It is a mighty cosmic engine that dwarfs planets and controls the motion of celestial bodies within our solar system through its gravitational grip. The Sun has enough gravity pushing inward to cause fusion. Its gravity is too weak to stop light from moving away, so we see the light leaving it. White dwarfs and neutron stars represent the remnants of devolving stars, where gravity compresses matter to extreme densities, but not to black hole type of density. Though small in size compared to the Sun, these objects wield intense gravitational forces. Some white dwarfs, like the 8.6 light-years distant Sirius B, have the Sun's mass packed into the size of the Earth. Zooming out to red giants, we encounter the largest known stars like UY Scuti with an estimated radius surpassing the 700 times that of the Sun. If it replaced the Sun, its surface would touch Jupiter. These colossal celestial bodies mark the pinnacle of stellar size, yet their gravitational fields remain dwarfed by the denser remnants like neutron stars. All of these stars are not dense enough to stop light from leaving. Thus we see them. That is why the black hole phenomenon is so special. Black holes are thought to arise from the gravitational collapse of massive stars. These would be much denser and smaller than the original star. Small black holes, born from the remnants of massive stars, typically range from 2 to 20 times the mass of our Sun. Their sizes are tiny, with event horizons on the order of kilometers. All black holes, small or supermassive, represent a cosmic oddity. They project a gravitational field that is stronger than the mysterious phenomenon that propagates light forward. Thus, light photons cannot leave the super-dense celestial body, creating the black hole effect. All gravitational fields weaken as the distance increases from the celestial body. We see this with stars and galaxies. The black hole is no different. A black hole's intense gravitational field weakens until the distance is reached where the light force is stronger. After that distance, the light photons can escape. This distance defines the boundary called the event horizon. The event horizon distance creates a spherical area, a shell surrounding the celestial body where light cannot escape. Outside of it, light can escape. Black holes much larger than the tiny stellar-sized black holes are referred to as supermassive. Supermassive black holes range in size. Sagittarius A's event horizon fits within the orbit of Mercury, while M87's event horizon is 4 times larger than Pluto's orbit. The universe exhibits 3 big classes of objects. There are celestial bodies that are too small to cause fusion, such as comets, planets, brown dwarf stars. The next class is the larger main sequence stars, which have a gravity high enough to cause fusion. These 2 classes bring us to a remarkable revelation. Black holes with their intense gravitational fields represent a cosmic class by themselves. They project a gravitational field that is stronger than the mysterious phenomenon that propagates light forward. The black hole class has celestial bodies that have several explanations. Black holes with 2 to 20 solar masses could easily be the remnants of collapsed stars. However, when we speak of supermassive black holes having 4 million or 6.5 billion solar masses, they are not the remnants of any one star presently known. Cosmologists have hypothesized that these supermassive monsters are stellar black holes that absorb the surrounding stars. They are the celestial vacuum cleaners. This reasoning is a logical explanation, but these supersized black holes could have a completely different explanation that has not yet been discovered. In conclusion, let us use the duck test. If it walks like a duck and quacks like a duck, it is probably a duck. The black hole phenomenon most likely consists of a central spherical mass, similar to a planet or star. Also similar, it is surrounded by a gravitational field that starts out its strongest and gradually weakens at farther distances. What sets the black hole apart from all other celestial bodies is its gravitational field is intensely strong. It is stronger than the force that propels light forward. Thus, initially, light cannot escape it. At a distance from the black hole's central body, the gravitational effect weakens to a level where it is now less than the light forward force. This is the event horizon distance. After that distance, light can leave or pass around it. Thus, a black hole is a superdense spherical body. It is surrounded by a shell area that ends with the event horizon. Beyond this distance, the gravity field gradually weakens until it approaches zero effect, similar to all other celestial bodies. Black holes have event horizons ranging from a few kilometers to billions of kilometers in diameter. The largest known is about 4 times Pluto's orbit. It is large when compared to our solar system, and tiny when compared to the distance to our nearest star neighbor. If we go back to the galaxy size level, the largest black holes are slightly larger than the largest star. They are localized events. No black hole has been detected near our solar system or nearby stars, so we do not have to fear them. They are another celestial oddity for us to study. This conclusion predicts many other ideas associated with black holes are unrealistic. Just because black holes are black and mysterious, some have suggested they could be a door to another dimension. Other ideas are that black holes are entrances to wormholes, tunnels that jump through space and time. In short, they are shortcuts to other distant areas of the universe. The proponents posit that we could fly into the black hole and instantly transport to another distant part of the universe. Instead, it would be like flying a spaceship directly into the sun. However, instead of crashing and burning, the black hole's intense gravity would tear us apart at the atomic level, and any material left over would add to its tremendous mass. Some have even imagined black holes were collections of organized constructions that make objects, celestial bodies or thoughts. They are the library of all celestial constructions. Then when the black hole later explodes, like the singularity and Big Bang, it will reform these objects of the universe. Whatever we cannot see directly stimulates our imaginations, similar to when in a totally dark room. But if it walks like a duck and quacks like a duck, It is probably similar to a duck. A black hole's central body is probably an overly dense spherical body, following the pattern of all other celestial bodies that we can see. What are your thoughts? Please leave them in the comments.